This is video number 3 for sections 1.5 and 1.6, the definition of a function. This is the other really important idea here at the end of chapter 1, this word function. This is a term that we will be using all throughout the semester, and so in this video I want to explain to you what we mean when we say function. I've written you a basic definition here. Function is a two-variable word, so we're talking about a situation where we've got two variables. How do you know if that situation meets the definition of a function? Well, a function is a relationship between those two variables, and here's the key, where one of the variables, often called the output variable, depends somehow on the other variable, often called the input variable. Now listen, we have been working with functions from day one. Okay, I wasn't using that terminology, but we've had many situations where one variable depends on the other. There were all those walking problems. Well, in all of those problems, my distance depended on how many seconds I had been walking. We had one with a bathtub where the volume of water depended on the time since the water was running. We had people at the beach, right, based on the temperature. And we said, oh, the number of people at the beach will depend on what the temperature is that day. So all of those examples were functions. Now, in order to make this a little bit more precise, we need to figure out what this means. What do we really mean when we say one variable depends on the other? And essentially what we mean by that is that if you provide an input, if you provide a value for an input, there can be no question as to what the one output is going to be. A lot of times people will draw a machine to represent a function. Let's say this was function f, a machine with an input slot and an output slot. Well, the only way this thing is a function is, if I dump something in, if I put some sort of thing in the input slot, there better be one and only one answer that comes out of this output slot for that particular input. In other words, each input better be matched with one and only one output. Let me say that again. We are saying to be a function, each input must be matched with one and only one output, or another way you could say that is exactly one output for each input. Well, let's play around with this a little bit. We need to try to put some examples down so that we can see when would you have a function and when would you not have a function. So let's take, for example, one of those walking problems that we did. Remember there was that one where it seemed like I didn't hear the person say go, and I just stood there for a couple of seconds. So let's say I stood there for 2 seconds, and all during that time I didn't travel any distance. And then maybe I started walking, and let's say I walked after that 4 feet every second. So by the third second I was 4 feet away. By the fourth second I was 8 feet away. By the fifth second 12 feet away, and so on. So here's a table that describes my times and my distances for that walk. And we're just trying to figure out, so is this a function? Yes or no? Some tables are functions, some tables are not functions. How do we decide? Well, it's all based on these definitions we just wrote down. You might pause the video and give it some thought yourself. Let me talk about some of the issues. When I do this in class, I'll ask people to share their thoughts. And usually the sticking point for people are these zeros right here. In fact, somebody will usually say, no, I don't think this is a function, because look, you've got this zero, and then there's a zero again, and a zero again, and that seems to mess it up. And while I know that those zeros are probably what your attention is being drawn to, in fact, this is a function. The answer to the question is yes, this is a function. You say, well, wait a minute, I thought we weren't allowed to have more than one output. No, you got to read carefully here. The two key words I would say in this little definition are these two right here. we're only talking about one input at a time. It doesn't matter that another input might use that output again. That's fine. It's just that when you stick in, for example, 1 second, there better only be one answer that comes out for 1 second. And there is. The only answer that goes with 1 second is 0 feet. When you say 2 seconds, there better only be one answer for that, and there is. The only answer for 2 seconds is 0 feet, and so on throughout this chart. Each input only is matched with one output. So what would a table look like that was not a function? Let's try to come up with one. It's not too difficult to do. Essentially what you would have to have is something like this. This particular table is not a function. Why is that? Well, because if I say, hey, I'm going to put in a 1, the inputs are always written on the left and the outputs on the right. If I say I'm going to put 1 into this function, what comes out? Well, half the people are going to say 3 comes out, and half the people are going to say 4 comes out. That's a problem. You cannot stick 1 in and get 2 different answers. Okay? So this would not be a function. I think a lot of times the way people remember this is by simply remembering that repeat numbers in the input column, that's what causes the problem. Repeat outputs, that's okay, but repeat inputs violate this definition. By the way, you'll notice I put X and Y here instead of T and D. That's because every single one of those walking problems that I did, those were all functions. They're all functions. This couldn't possibly be a walking problem because it would mean that after 1 second I was 3 feet away as well as 4 feet away. Well, that's impossible, right? I can only be in one place at one time. So all of those were functions. Okay, let's try graphs. So what if I had a graph and I'm looking at it, an XY graph? How do I tell whether or not that graph is a function? And the example I thought I would use, maybe you've done this kind of graph before, it's called a parabola, kind of a curve that goes off in both directions like that, a parabola. We'll study those later in the semester. We're just playing the same game, yes or no, is this a function? Well, the test is everything, right? What I have to figure out is for each input, in other words, when I pick a specific input, like here's one, 2, the inputs are the x's. The inputs would always be on the horizontal axis, the outputs on the vertical axis. When I pick an input, how many outputs are there associated with that input? Well, I only see one. It's right here, right? I don't know what that number is. Let's make something up. Let's say this is 2, 4, 6. Looks to me like when I put 2 in, I get 6 out, and that's the only thing I get out when I put 2 in. Well, you can try that for other x's. Doesn't matter what x you pick, there's only one y value on this graph that is matched with each x you would pick. And so the answer is yes, this is a function. So what would a graph look like that is not a function? Well, a famous example would be a circle. We will get into circles way at the end of the semester. But let's say we looked at the graph of a circle. Well, look, now, if I pick an x, like x equals 1 here, do you see that that particular x is matched with a y up here? But then it's also matched with a y down below, right here. So that one x is matched with 2 different y's. I don't know what the number is. Let's say this was a 3 and this was a -3. Well, now if I say, hey, when I put 1 in, what comes out? Some people are saying 3, some people are saying -3. That's bad. This is not a function. If you've done this before, you remember that there is a test, a very visual test that you can use to determine whether or not a graph is a function. The test is called the vertical line test. And it goes like this. Take your graph and start drawing vertical lines, either physically or just imagining it, if those lines always cross the graph just once, then we say it passes the vertical line test and it is a function. But if you start drawing vertical lines and you ever come to a point where you're hitting it twice or more, then it fails the vertical line test and we know it's not a function. Why does that test work? Well, because it just demonstrates if it fails, it shows you that, aha, here's an input that actually gets matched with two different outputs. Some of you, when we were looking at the parabola, may have been bothered by the fact that some of the outputs repeat each other. But remember, we covered that in the example with the table. It's okay to have repeated outputs. You run into problems only if the same input is matched with two different outputs. All right, and then finally, what about lines? This chapter has been all about lines. Are lines functions? And the answer is most of the time. So here's what most of the lines have looked like that we have been drawing, and the one I just drew there, absolutely. You could imagine doing the vertical line test, and if you start drawing vertical lines once, right, you're never crossing it more than once. So absolutely. So is every line a function? Well, there is just one type of line that would not be a function. You can think about what that would be for a second. If there was ever a graph that fails the vertical line test, it would be a vertical line. I mean, that is the ultimate failure of the test. If you draw a vertical line through this graph, it doesn't just cross it twice, it crosses it an infinite number of times. So this would be an absolute fail, meaning vertical lines are not functions. Remember, vertical lines mess everything up. Those are the ones where the equations don't even work right. They don't match y equals mx plus b. They're just x equals a number. They don't have any slope. They don't have any y-intercept. They're not functions. They're very much the exception to what happens with most of the lines. Most of this class is really about the topic of functions, what they are, different kinds, and how they can be used in real-life settings.